Deriving the formula for simple harmonic motion. Consider a mass m which slides over a horizontal frictionless surface. Suppose the mass is attached to a light horizontal spring whose other end is anchored to an immovable object. Let x be the extension of the spring. Equilibrium state would be the position of the mass where no force is exerted on it. If the system is disturbed from its equilibrium state, then the mass experiences a restoring force. The restoring force is equal to kx, where a negative sign would indicate that the direction opposes the direction that the mass has been displaced. If we use Newton's second law, we see that F equals ma becomes negative kx equals ma. Knowing that a is the second derivative of x, we can write this as a second-order differential equation. A differential equation because the variable and its derivative are in the same equation. Second order because it is the second derivative of position x. To solve this differential equation, we need a function that's a second derivative that is always proportional to the variable. Consider the functions you know. What function, if you take the derivative twice, is proportional to its original function? Remember that the derivative of sine is cosine, and the derivative of cosine is negative sine. So either the cosine or the sine function will work. If we take the position function to be a sine function, where a represents the amplitude or the maximum displacement of the mass on a spring, and omega refers to the angular frequency of the function, then the first derivative would be a omega cosine omega t, and the second derivative would be negative a omega squared sine omega t. Notice that the position function is proportional to the second derivative of the position function. We can plug in these functions for x and x double prime. Here we are with x and x double prime plugged in. We can now do some algebra and simplify. Which leaves us with omega equal to the square root of k over m. Consider that in a full oscillation, a cycle goes around 2 pi radians. We can use this to find the relationship between angular frequency omega and period or length of time it takes for the pendulum or mass on spring to complete the full oscillation. Omega is equal to 2 pi divided by the period. We can use this to solve for the period of a simple harmonic oscillator. As t equals 2 pi times the square root of m over k.